Hello and welcome to Deep Dive. I'm Dr. Jasmine Walia and today we are going to talk about thorium reserves and the race for energy dominance in the world. Imagine a mineral so potent that it powers a country for 60,000 years, cleanly, safely and sustainably. Recently, China has made headlines with the discovery of nearly 1 million tons of thorium at its Bayon Obo mining complex in Inner Mongolia. This wasn't just a resource find, it marked the beginning of potential global energy shift. What made this even more significant was China's parallel effort to build the world's first commercial-scale thorium molten salt reactor by 2029. In this VisionIAS Deep Dive series, we unravel the whole scope of this story. We'll start with talking about what is thorium. Why does it matter? Where is it found? What can it do? What hurdles does it face? And most importantly, what is India doing about it? Let's begin with understanding the element at the heart of all of it. Thorium is a naturally occurring radioactive metal primarily found as thorium-232. It's 3 to 4 times more abundant than uranium and is mainly extracted from the monazite sands, often as a byproduct of rare earth mining. Unlike uranium, thorium isn't itself fissile, but it's fertile, meaning it can be converted into uranium-233, a fissile material capable of sustaining a nuclear chain reaction. Now, what makes thorium as attractive as a fuel in the future? Firstly, I'll say safety. The thorium reactors, especially molten salt reactors, operate at low pressure and are less prone to meltdowns. Second is the waste. Thorium produces significantly less long-lived nuclear waste compared to the conventional uranium reactors. Third would be the non-proliferation. Uranium-233 generated from thorium is contaminated with uranium-232, whose gamma radiations make weaponization highly difficult. Lastly, energy density. Thorium offers a much higher energy output per unit mass than uranium. These benefits don't just offer a technical upgrade, they reshape how the world might think about nuclear energy. And that brings us to the next vital question. Where can we find thorium? Thorium is scattered widely across the globe, but its extraction and use have been limited by policy, technological readiness, and economic feasibility. India, Australia, and the United States possess particularly large reserves, with India often cited as holding 25% of the world's thorium. This is primarily found in the monazite sands found across the coast of Kerala and Orissa. China's thorium discovery at Bayon Obo, estimated at 1 million tons, is set to rival even India's long-standing dominance in thorium resources. In addition, countries like Brazil, Malaysia, South Africa also host significant thorium-based deposits. While thorium is present in trace amounts in soil and rocks globally, commercially extractable reserves depend on associated rare earth mining. This makes thorium more of a strategic byproduct than a primary mining target. However, with rising demand for clean energy, this may soon change. Now that we know thorium is abundant and promising, let's explore what exactly it can be used for. From energy to industry, historically, thorium has found its use in gas mentals, welding electrodes, and scientific lenses due to its high melting point and luminescent properties. Today, however, its most significant application lies in nuclear energy. Thorium can fuel molten salt reactors, which offer steady baseload power with reduced waste and enhanced safety features. India and China are working to integrate thorium into their nuclear roadmaps. Beyond power generation, thorium reactors are being explored for maritime use, especially in powering large container ships. This could revolutionize shipping with low-emission, long-endurance reactors. In industrial domains, thorium compounds improve high-temperature strength in alloys and enhance the efficiency of catalyst. The thorium dioxide is used in refractory ceramics, aerospace components, and high-index optical lenses. While non-nuclear applications are declining due to radioactivity concerns, nuclear-grade thorium use is gaining traction. The potential is vast, but it doesn't come without significant challenges. Let's understand what's holding thorium back. Despite its advantages, thorium faces several scientific, economic, and political barriers. First of all, it isn't fissile. It requires a driver fissile material like uranium-235 or plutonium-239 to start and sustain a chain reaction. Secondly, the reprocessing of bred uranium-233 is chemically complex and radiologically hazardous due to the presence of uranium-232 and its decay products. Third, thorium extraction is costly. As a byproduct of rare earth mining, it's not currently mined independently. This makes thorium economically unviable without a parallel demand for rare earth metals, rare earth elements. Fourth, the lack of infrastructure. Most of the global nuclear facilities are optimized for uranium-based systems. Shifting to thorium would require a massive investment in reactor design, safety validation, and fuel processing. Then we have regulatory and research inertia. Given uranium's head start, there's limited operational experience with thorium. This results in higher uncertainty and slower licensing and deployment. Despite these challenges, the potential rewards are so vast that major countries are making serious investments. Which brings us to our next section. How is India responding? India's nuclear strategy has long envisioned thorium as its end goal. The country's three-stage nuclear program begins with a pressurized heavy water reactor, moves to fast breeder reactors, and culminates in thorium-based advanced heavy water reactors. India's thorium potential lies in the large reserves and research ecosystem. The prototype fast breeder reactor at Kalpakkam has marked the beginning of the stage 2 of this vision. Once it achieves criticality, it will produce plutonium needed to convert thorium into uranium-233. Additionally, India has partnered with Clean Core Thorium Energy to develop a fuel by blending thorium with low-enriched uranium to retrofit existing reactors. The Department of Atomic Energy continues to refine design and with the aim of commercializing thorium reactors by the middle of the century. While India's progress is cautious, its roadmap remains scientifically robust. But the question remains, will India scale fast enough in the rapidly changing world? The energy future is at a crossroads. Thorium presents a fork in the road, one that leads to safer, cleaner, and more equitable energy systems. China's discovery and aggressive deployment strategy may grant it dominance, but not just in energy, but also in the strategic nuclear export and maritime logistics. India, with its legacy of thorium reserves and the vast thorium reserves, has the opportunity to lead if it accelerates. The thorium story is not just about a metal, it's about energy sovereignty, technological leadership, and climate resilience. As the world moves beyond fossil fuels, thorium may power not just the reactors, but a completely new world order. I hope you found this topic on thorium interesting. Please stay tuned for more in Deep Dive.